Hello, I'm Byron Liang from TUV Rheinland. Are you familiar with lawn mowing? What does an ideal robotic lawnmower consist of? The initial design include the boundary wire, the electromagnetic signal of which is detected by the internal sensors and defines the working area of the robotic lawnmower. The robot is also made up of microcontrollers, interactive switches, power circuits, battery management system, and motor driver. Those modules and components build up fundamental architecture of nearly 80 robotic lawnmowers, especially in European market nowadays. When integrating the positioning system, machine vision or LiDAR, a wireless robotic lawnmower with virtual boundaries is created. So, how do various robotic lawnmowers with different designs perform? Let's go to the TUV Rheinland Household Robotic Lawnmower Performance Challenge. TUV Rheinland builds a professional testing field with an area of 3,600 square meter, which plants with Bermuda grass, ryegrass, manila grass, and tall fescue. The testing field include a standard lawn of EGMF of Stiftung Warentest particular sites for durability testing area, maze map, slot map, and dense grass area. Let's welcome Mr. Wang from TUV Rheinland to introduce the competition.
The first Household Robotic Lawnmower Performance Challenge consisted of 4 major events. The first one was Mowing Challenge, which was conducted in the standard lawn of Stiftung Warentest. The mowing path was tracked by the positioning system. The real-time screen showed the working status, such as working area, real-time lawn coverage, etc. After fully charged, the robotic lawnmowers started working from the charging station. We can see that the coverage of robots with random path increased rapidly in the early stage, reaching up to third in less than 1 hour. For the robots with path planning, the lawn was cut by different small regions by horizontal direction or by oblique direction with parallel lines. The covering capability of path planning robots surpassed those with random path by 2 hours. After mowing for 6 hours, the lawn coverage of path planning robots became much larger, reaching 87.3, 84.6, and 79.1. The mowing efficiency tested above plays an important role in product design, as it is one of the selling points for a robotic lawnmower with path planning.
The mowing performance in dense grass areas were also tested. The grass used in this test was manila grass. For the cutting from 70mm to 60mm, one stopped working among 11 robotic lawnmowers. Another 3 robots were stuck after cutting from 60mm to 40mm. For the cutting from 60mm to 30mm, only one robot continued mowing without being stuck by the thick grass. If following the guide of cutting 1/3, most of the robotic lawnmowers can work normally in dense grass areas. However, for the lawns with tall and thick grass in North America, the robots nowadays still encounter big challenges. Meanwhile, the grass clippings cut by brand new blades were collected. Some of the clippings were neatly cut while the others were partially or completely torn.
It should be noted that torn cuts will adversely affect the health of the lawn. Here we come to the second event. Durability Challenge. The test was conducted in bumpy ground and lasted for 100 hours. Some robots occurred design or quality issues such as wheels being broken, floating shell loosening, sensor malfunction, and abnormal motor protection, etc. The third event focused on driving performance, especially in slopes and concave ground. Among 11 robotic lawnmowers participated, 3 of them can handle slopes larger than what they claimed for. 4 worked fairly on the claimed slopes, while the other 4 failed to go up the expected slopes for the concave ground. 1 robot was stuck at a 10cm depth adult footprint. 2 got stuck in a circular pit with a diameter of 1 meter and a depth of 10 centimeters. The 4th event was Maze Challenge. The first part of Maze Test was obstacle avoidance. Apart from the obstacles originally built in the test field, some specific objects were added together. This test was only conducted in 8 models with non-contact detection sensors and in sunny days with light intensity of over 10,000 lux. We found that only 1 model with camera could detect and avoid all the obstacles successfully. The second part was Maze Test. The maze was made of narrow paths, corners, and small regions with different size. After testing for 2 hours, only 1 model could go through and cover all the areas. The maze test showed the comprehensive capabilities of obstacle avoidance, positioning, and path planning to a certain extent.
The first TUV Rheinland Household Robotic Lawnmower Performance Challenge has come to end. We found additional issues beyond the above. For example, the robot dragging the chair, the robot sliding down the slope, obvious wheel tracks the lift sensor being activated unexpectedly, the blades being broken by cutting slabs, the grass left uncut, too much clippings sticking to the machine and getting stuck on wooden stakes. Meanwhile, more tests need to be added. For example, testing the precision and offsets of the satellite signal, testing on multi-zone areas, adding more typical objects as obstacles, and building up typical European and American private yards as testing fields. Last but not least, TUV Rheinland looks forward to collaborating with all of you in exploring the higher performance of robotic lawnmowers. We wish all the robotic lawnmower partners a prosperous career.
TÜV Rheinland.